Bienvenue au 5e édition de Hack in Paris. I will now go to English, which is much easier for me. How many of you, is this your first time here? Whoa, a lot of newcomers. Sistrine puts on an incredible show. You're going to have a lot of interesting people to talk to, a lot of great presentations, and please, we have a lot of sponsors that have helped out to make this all possible. This is the new facility. What do you think of this new facility? Isn't it great? Yeah, I mean, I absolutely love it. I think this is, yeah, let's hear it for him. So, without getting by, we're going to be running a little behind schedule today, as you can tell, and that's okay. We will try to make up some time, and during the first break and during lunchtime. Keep in mind that around 5 o'clock, we will have a debate, a very hot debate on vigilantism and strike-back active defense in cyberspace. So please make sure you're here. We will have alcohol for that and make it all the more interesting. But I have the honor of beginning this conference, and we're going to talk about something that perhaps is new to you, and I have talked a little bit about it in the last couple of months, mostly in Europe. And I'm going to mess with your minds a little bit. I'm going to present an idea, a series of ideas that may be right, they may be wrong, but whatever, hopefully they can give us a new perspective, a new view of information security. Because certainly some of the things that we've been doing over the last few years have not been working. So let's keep in mind APTs. People are owned for hundreds and hundreds of days. The concept of digital is something that we live with, something that we breathe in our world, and I want to change that a little bit and get you to think about the concept of analog with a few fundamental concepts. That why does digital have to be binary? Why do we treat security as though it's one thing only, that it's static? Where are the measurements of security? I don't know if there's any vendors here, but how many times do we get a product from a vendor that has a guarantee of performance, that it will work? Not very often, if at all. And we're going to present some ideas. I have stripped out most of the mathematics, because that is things I do at B-sides that are 4, 5, 6 hours long, to give you the high-level view. So right now, security is keeping the good guys honest. That's about it. Oh, wrong button there. Legislation and laws about security. How do those work for us? Those work well? All the laws and compliance. Now we're building IoT. We already have a mess, and in the next 10 years, we're going to add 20 billion, 30 billion, 40 billion new devices onto something that's already broken. Something has to change. So I grew up doing this stuff. I was a TV repairman at 5 years old, which was very, very easy back in those days. You take everything out of the TV, go to the drugstore, find out what broke, replace it, and almost anybody could do this. But I had a deficiency. I'm colorblind. I don't see color very well. And as we go through this, you're going to see how this influenced my thinking when it comes to analog processing and the differences between analog and digital. I grew up in rock and roll. I was an audio engineer, and I worked with all the great guys, and you see the console on the right there, hundreds and hundreds and hundreds of analog control devices in order to make music. That thing with the 3 dials, that is an analog computer from 1962, 63. Yeah, it kind of worked, but it was a different approach that I'm going to suggest we start revisiting again. So, analog. WTF, what is it? Well, can you read those? It's kind of difficult. These are some questions, and the slides, I will make them available to everybody. What is analog? Is analog always a yes or a no question? When a lawyer asks a question, did you kill that person? Is it always a yes or a no answer? Or is there something that balances? When we look at balance, it's analog. It's not yes or no. Analog means something very simple, continuously variable, changing all of the time. And in the analog world, we take digital signals and we put smoothing functions on them to make them look better and ultimately sound better. When you watch a movie, is it analog or digital? Anybody? Is it analog or digital? 30 frames per second. It's a digital function that our eyes and our brain processing turn into an analog signal to make it look continuously variable. When we talk about things like Asperger's syndrome, he has Asperger's. Well, there is a spectrum. It's not a yes or a no answer. And I've started to approach security with this same kind of approach, trying to look at it and see, are there new answers that we can come up with if we just look at the universe completely differently? I also have a thing called synesthesia. And when I was in the record business, I saw music. So we were recording concerts or recording an album in the studio. I would see colors, and this is often the kind of image that I would see while we were making the music, and it somehow helped me do it. I'm going to also suggest that the internet has become analog. When we look at one endpoint, that might be digital, it might be binary, but the internet as a whole, including what's coming with IoT, it's a constantly changing blob. Do we really have perimeters anymore that we can say are defined digital points? And I'm arguing that when we step back and look at large networks, look at how everything is connected, that it is really much more of an analog function when we want to think about how to make things different than they are now. The brain is analog. The brain is not a computer. The brain is a great averaging machine. It averages everything. When you see something and you're looking and it's very, very clear, less than 3% of your brain and your eye are used to do the focus. Everything else is fuzzy. But the brain averages this, and we're treating the world, how do we interface with that from a human standpoint? So now we're getting the bioimplants and the prosthetics, neural implants, where we have to connect the digital world that we're growing up in and we now know with the analog human element. And more of this is coming. I think Elon Musk is leading now, saying we have to be very, very careful how we become the Borg as we put all these things together. So let's step back and see, how did we get into this mess that we're in right now? And the fundamental security model that we use today was developed in the 1970s. We still use it. And it was based upon mainframe computers. And the mainframe computers had a box, one wire, and a green screen. And that's how we did security. Security was done with a static mindset because the military are the ones who developed it. So when we look at military history, the Maginot Line did not work. The Great Wall of China did not work. Berlin Wall. Anything that is a static defense in the military world has never worked. But that's how we chose 40-some years ago to actually build security into our computing infrastructure such as they were. And it's based upon the concept of risk avoidance. I want no risk. So the concept was build the walls higher, and that'll keep the bad guys out. In what we do today, we say, let's add more firewalls, more controls, more defensive technologies, and that'll keep the bad guys out. That works, right? Come on, I'm getting a no from everybody here. This is what we have chosen to do. And the fundamental mechanism is called the reference monitor. And there were several people involved in the development of it, Anderson, Beebe, Bell, and LaPadula, back in the 70s. And it was very simple. We're in a one-directional communication called asynchronous. And what we did is a system request would come in, stop the process, go to the side, make a decision, come back, and it had a yes or a no answer, a binary answer. Now this worked in a mainframe environment. What killed it all? The concept of network, because a network is synchronous. It goes in two directions. And this was an asynchronous model that only worked in one direction. Yet we have stuck with this model because we started building technologies around that concept, and that's why every vendor today has a next generation thing that is really going to fix your problems. We're stuck in this mindset. So a number of years ago, a friend of mine, who will be in the debate hopefully this evening, gave me an idea that I started working with, and it was called Protect, Detect, Respond. And he developed it for the United States Department of Defense. So one of the questions that we began with is, here's a vault. Is that vault secure? Is it secure? Jason, is that vault secure? No, why not? Because the door's open. If the door is closed, is the vault secure, Jason? No, why not? He's going to get somebody that's get the combination. So he's going to do the social engineering thing. But technically, in the physical world, we have something, and we do something for security we don't do in our world yet. A safe, a vault, has a rating. And the rating is temperature and time-based. How long will that metal sustain a torch trying to break through it? So when you ask your vendor, your firewall looks really nice. How many hours will it protect me against the Chinese? Are you going to get an answer? In the physical world, we have the answer. But in our world, we don't have it yet. And I'm going to argue it's about time. And we're going to use time throughout. And time is an analog function. It's continuously variable until you get down to quantum mechanics, and we're not going to do quantum mechanics here today. It's all about time. So we can't rate our firewall. Nobody knows. All the vendors lie. No offense to vendors or supporters, of course, but that's what sales and marketing guys do. Ours is the best. Ours is the best. But they all operate on the same fundamental principle. When we look at firewalls and access control mechanisms and protection devices, ultimately, do the bad guys go through the front door trying to beat it? They do what was done around the Maginot Line. They go around it. They go over it. They'll dig under it. Protection devices is where we have invested hundreds of billions of dollars in the last 25 years, and it doesn't work for all of these sorts of reasons. So we need to take another approach. What can we actually measure in our networks? And what we can measure are two things. One is detection. And a detection could be in the physical world, a sonic alarm. It could be the tape on a window noticing that the glass has been broken. We know how to measure the amount of time it takes to be able to detect something. And I know a lot of folks, and I don't know if any of you have, actually built and run some code in your networks, hostile code, as a test to see, number one, can your detection mechanisms pick it up? But number two, how long does it take? But detection is only half the battle. We have to be able to react. And in the physical world, maybe a jewelry store is getting robbed. The alarm goes off right away, very, very, very quickly. How long does it take police to show up to actually do something? We can measure that. And in your networks, you have the same capability, depending upon how your reaction to a detection works. Do you send somebody an email? They get an SMS? They get a telephone call? What if the guy is on holiday? What if it's the weekend? Are there 5 people to react? How long does it take? You have the capability right now to be able to do some very simple code and test your own networks to begin to get a metric, a measurement of how secure you are. And we're going to get a little more refined in this. And ultimately what happens, and I'm not going to go through crazy math with you, is it turns out that we can measure and quantify security with a simple formula. If my firewall, for example, is strong enough to be able to take somebody hacking it, but that amount of time is greater than the amount of time it takes my detection and reaction mechanisms to find out what's going on and then do something about it, I then can have a secure environment. And I'm using exclusively the time domain to be able to do this. So this is something you can do right now to find out where you are, because something very interesting happens. In the Cold War, we did exactly the same thing. If the United States or our allies detected in the Cold War a Soviet missile launch, we had 18 and a half minutes to make a decision as to whether to shoot back or not. A time-based function in the physical world, which gives us a lot of hope for what we're trying to do in our world. So when we're looking at our detection and reaction, there's little components of it that will work in one way if you have a manual operation where the human has to get involved, or it'll go much faster if you have an automated process because you have planned out things in advance. And in my experience, the number of companies that have actually planned out responses to security events are very, very rare. They like to call in the lawyers. They like to call in the police. They want to call in management to make a decision, which makes the detection time and reaction time much bigger, which means that my protection metric is that much smaller. Some very, very simple concepts that we're going to play with. But what this gives you is an opportunity to measure your exposure time. The exposure time is your detection time plus your reaction time, because we know that protection cannot be measured. So we put on a risk management hat and look at it that way. And then we can do some math and let the guys over, not in security, but the auditors, the financial people, you can now, when you go home, measure your network and determine your exposure time to find out how much damage can be done in 5 minutes, 10 minutes, 2 hours, or in cases of China and APTs, 400 days, 600 days. We are missing the entire point of what protection really means. And a part of the problem is, obviously, people do not know what they have on their networks. And we tend to look at our networks as one single thing that everything under the hood has to be protected. Everything has to be protected, because that's the technology that we have been given thus far to be able to use. But is everything of the same value within your network. And obviously it's not. Some things are much, much more important than others. But we're still seeing the same security problems regardless of how sensitive that data may be. Now we can also apply the concept of defense in depth with this simple concept. We go to the movies and we see the big house on the hill and the bad guys are going to rob it. So as they want to rob it, they notice that there is an alarm system. So what do? They want to disconnect the alarm system, obviously. However, with defense in depth using this model, I can add an additional layer of protection, detection, and reaction to the primary detection mechanisms, which will give us increased levels of protection with some defense in depth. But I am not at all convinced anymore that I believe in defense in depth, and I'm going to show you how that works out and why. The other thing that you can do with the exposure time is to determine the file sizes that could be actually targeted. And it's fairly simple math to figure out where is my weakness, what is susceptible. And with padding solutions, with adding additional bits and bytes to files, through obfuscation of them, through encryption, etc., we can then say certain files have a higher level of probability of being attacked, being exfiltrated, and then we can start mitigating and handling this in a slightly different way. But this is only the very beginning of where we go. The circuit in the top there is an analog circuit that dims a light bulb. That's all it does. Very, very simple circuit. But what we don't do is how come we don't dim all the data when we notice something? We have the ability currently to add what is called a bandwidth limiter. It's a simple analog concept that came from the music industry that we can apply to when an event is occurring. Because we tend to these days say, oh, something's bad happening, turn it off, then we'll fix it. I'm saying there's a middle ground by dimming the amount of data. And again, it's a time-based function, analog function, and something really interesting happens, and hopefully you can read some of that, that if I restrict the bandwidth, if my bandwidth is normally 1 gigabyte, and I sense something going on through a detection mechanism, but I don't want to shut down my company, I don't want to shut down accounting, I don't want to shut down my transactions. What about bandwidth constriction? The numbers turn out very, very interesting. With a little bit of bandwidth constriction, my exposure time will remain the same, but my data exposure will go down orders of magnitude with a simple, instead of turning it on and off, just restricting the amount of data that goes through it. Now, the bad guys know math. These guys are not idiots. And they understand just as well as we do. Just because they work for the bad guys doesn't mean they're idiots. But they're also understanding that there's a lot of math that's coming up, and we are redefining what security is. So one of the things that really bothers me in our technologies today is the concept of root. Anybody hate root control as much as me? Yeah, I'm getting some heads. Root, it's one person with total binary control over a system. One person. One person. And I have a problem with that. And whether you look at a Snowden event, you look at an insider gone bad, an administrator overriding a manager, whatever it is, root control gives us. How do we get rid of root? Well, right now, a little Boolean algebra, right now we have multiple administrators in single processes. We have to, because one person is not going to work 24/7. So we end up with a Boolean OR. And the Boolean OR says either administrator A or B can do whatever it is. This is the way we do things now. Now, when we have multiple administrators having access to root, what happens to our security? Does it go up or down? It goes down. And there's a lot, again, math, I'll be happy to share all the math with everybody. The security goes down significantly, and we use probabilistic math, simple calculus to do it, to determine the hard numbers. So this is where we are today, and we know it doesn't work. In the enterprise, how many are there? I don't know. There's a bunch, and every company is going to be slightly different. So this comes into the factor of trust, and we're going to look at trust a little bit more, because currently we have a trusted employee. But when you have a trusted employee, do you trust him 100%? Again, a binary function that we're using. I trust him, I don't trust him, so I give him complete control or no control. How do we begin to solve this? Well, in a safety deposit box, we use a thing called the two-man rule. Two different people with two different keys have to unlock the contents. And the two-man rule works pretty well. Now, from a logic standpoint, the two-man rule is an AND gate in Boolean speak. And on the top row, there's two levels of control. So in this case, both Administrator A and Administrator B have to both approve whatever the action is. And it doesn't have to be at admin. It could be anywhere from code, because this will work at the code level all the way up to BGP. The problem with this, though, is time. Because while Administrator A may say, okay, I want this done, Administrator B may be out to lunch, he may be on vacation, he may not agree, there may be a dispute, and suddenly the attempt to make a control change is nullified. It does not work. So we have to find a way around this. So this gets back into trust, trusting your partner. Do you trust your partner with your life? Do you trust your partner to write a check without your approval? Banks use this as well, the two-man rule for major financial services. And this is the world we live in today. So how are we getting around this? By looking at trust factors. Currently, most human resources and hiring departments and managers do not use a matrix to look at how trustworthy is somebody. And this becomes very important when they're hiring. If you're going to hire somebody who is going to do some really deep analytical coding, but he may not have access to administrative controls, does he need the same level of trust in the system as somebody else? Again, we look at it binary, yes or no, without coming up with some of these numbers. And these numbers can change throughout the life cycle. That's why we had Robert Hansen and Audrey James as spies in the United States, because security services and the FBI and the CIA never rechecked these guys as to why they were spending millions of dollars. So again, they approached it from a binary, static standpoint with no change at all. Now we're going to introduce another concept before we start gluing this together, and it's called feedback. And in the military, it's called the OODA loop. Very simple. Observe, orient, make a decision, and then act. And this was developed by Colonel John Boyd in the 1980s in the United States. And it was done for aerial combat. The same thing applies to marketing and sales. I have a product idea, I'm going to test it out, I'm going to make a decision to make blue widgets, and then I'm going to re-observe. Look again, see how the market likes it, and change it. And we call it squeezing the loop, where I want that loop time to shrink and get very small. The same way that I want my detection time and my reaction time to get very small. And in calculus terms, all this is a limit function. Very simple to be able to work with. So I want to squeeze the loop with whatever process I'm doing. And if you want to apply defense in depth concepts, there are subloops that can be applied, and this is where it gets very interesting with fractal analysis and understanding the dimensions of your networks. And again, I'll help you with the math later on. Now, feedback is inherently analog. In the world I grew up in the upper left, we've all heard squeals when the microphone on the speakers, you know, it's feedback. The device on the right, that is a mechanical governor to control and regulate the speed of an engine, and in this case from a steam engine from the 18th century. In the lower left, it's an electrical circuit, the fundamental circuit for all analog circuits is negative feedback controlled in order to keep things from going what we call a runaway condition, where things get chaotic, when you lose complete control of the system. Sounds like digital networks that we're living in today, but in the analog world, we solved it many, many, many years ago. In fact, in the 1920s. ICS, industrial control systems, many of them use this, and I'll show you how that works in a little bit. The other component of feedback is haptics. And we hear, okay, the new phones, they buzz, they're tactile, you get a keyboard, it goes click, you feel it. On the new smartphones, sometimes they'll vibrate a little to let you know what's going on. We as humans require feedback, and it is built into every aspect of nature, built into every industrial control system, every piece of analog electronics on the earth, and it works. But we don't do it in networks. We don't do it in our world at all. So what we're going to do here is take a very simple example, and in this case, we'll use a password. We're going to log in to something. And all I'm saying at this point is, let's introduce an analog feedback loop into my digital processing. So when I make a decision, I take an action, whether it's, again, at code level, administrative level, doesn't matter, all I'm doing is starting a clock. And that clock could be 3 milliseconds, 3 microseconds, 2 days. It doesn't matter. It's a decision that has to be designed into the system. How long do I require the time to be before somebody else actually approves that primary control choice? And this is the first step of making all analog work. And in this case, we've got administrator A making a decision. In the construction of the system, they've set a number, could be 1 hour, where administrator B has to finally make the approval. If he does not do the approval, the original decision is taken back and completely rescinded. So when we move this forward even into greater levels, we can do this at the access control level. We can do it at the code choice level. We can do it in virtually any environment. Now, some of you may know this in the physical world. You go to your office, open the door, but you have a security system. So you have to run like hell to the closet, open the door, and enter in a code within 30 seconds, perhaps. Again, we do it in the physical world. We know that it works, but we don't do it in our world yet, and all we're trying to do is to look at it from perhaps an INA mechanism standpoint. It's exactly the same process. Any access control mechanism will do the same thing. And what we do is take this and apply a fundamental bit. Now, the fundamental bit of unit in Boolean logic and in digital electronics is, how do I store one bit of information, either a 0 or a 1? The way it's done is through this circuit, and it's called an RS flip-flop, and there is the logic table as to how it works. And very, very simple concept. Admin A is at the top, he does the reset, or admin B can do a set, and it changes the output, digital. This is the way we're doing things right now. But what if I take that same circuit and I apply a feedback loop that's analog to it. What do I have? I now have a new set of truth tables. A set of truth tables that are digital logic with a time-based component to it that it can be preset in any environment we're dealing with in our digital world. That's the logic symbol for it that has been developed. And there is the truth table for it that gives us more conditions than we had before, because certainly it is a little more complex. But all of the enabling of this is just part of setting up the risk that you're willing to have in your network based upon exposure time and your detection and reaction from early on. Now, how do we launch a nuke? Again, something that we've been very used to in many countries over the years, and this is the two-man rule. The circuit for the two-man rule on how that works is this. It's very, very simple, and it's applying how much do I trust Administrator A versus Administrator B to initiate a launch sequence before the second guy can go, yes, I approve, or no, I don't approve. This is the fundamental circuits that will do this, and we're having it coded now, and we're going to be giving it away for free for anybody to be able to apply this. The next thing I want to do is to take a concept we used in the audio world when digital audio began in the 1970s. Traditionally, as you saw in that earlier circuit, I'd have a volume control that is directly in the circuit. That matches what we do today with TCP/IP. My single level of communication, the TCP/IP channel, goes over one physical transport level, and that same communication channel is synchronous, but it has both data and the control signal. Back in the 70s, we realized in the audio world that's not going to work anymore when we're doing automation. So what we created was an out-of-band mechanism to be able to vary the amount of signal that went through any particular circuit, an analog function. Part of the great part that occurs here is that if my data, my audio signal dies, okay, I've lost my audio, I've lost my data, that's fine, but I still have my control. If I lose my control signal, because it is a fixed out-of-band control into that circuit, I will not go into chaos. It will remain the same, will not change until the control signal has come up. And this is talking about going out of band. How do I get out-of-band circuitry to be able to work and communicate where I don't have to rely upon the TCP/IP channel to do my detection and reaction, especially when we have hostile bad guys. We're looking at DDoS attacks, some of these major level events that are occurring. How do I do something about this? Well, we want to have some time-based escalation. And what you notice in this very simple network here is that there's some routing channels, but then you notice there's a lot of sensors. A lot of sensors. Anybody know how many sensors are inside of a jet engine today? About 4,000. 4,000 of them that generate constant feedback of information and generate between 1 and 2 terabytes of data, sensor-based engine performance data, every hour. We keep the planes flying using a very simple analog feedback technique. And we use a concept that I said I disagreed more and more with, the concept of defense in depth. I am getting very impressed with the idea of detection in depth. We need a boatload more sensors in our networks at all levels, at all layers of the stack, all the way down and all the way up through everything we're doing, and inside of applications as well. But in order to do that, as I mentioned earlier, we have to have reaction. We have to know what we're doing. If this is going to work, people have to be willing to plan out and understand how bad things can be and what should occur. If we don't take this step and we allow management to continue doing it the way it's being done today, we're going to continue to fail. So there's lots of small elements to make this all work. We have a single reaction channel. That's certainly possible. We've got detection in depth with multiple reaction channels, the same kind of concept. And we take the same out-of-band concept, and let's say we're doing this at the BGP, at the ISP level, creating an out-of-band network just for security, will allow us then to have ISPs talking to their peers, and it's peer-to-peer conversations, there are not that many of them, and be able to do honest-to-God tracking back to the source and mitigation of spam and hostile attacks at this level. It looks fundamentally like this. I've got my primary channel of data communication. I'm using TCP/IP. I can use it as a control signal. But when something goes wrong, each one of those points at the sensors is going to need to have a detection module, reaction module, and then back channel communication through out-of-band. The other thing that we can do with our circuits is something that back in my day we called negative time. What if I introduce negative time into some of my circuits when decisions are being made? The negative time factor, there's the schematics for it. These are not things that have to be invented. These are things that have to be rethought. And it's called introducing intentional delays into circuits of a few nanoseconds for the processing and decision-making to be done. Because if I know my detection and I know my reaction time, that becomes exposure time. If my exposure time is very, very small because I've done it right, and I add a little bit of negative time delay, what happens? Mathematically provable security. Mathematically provable security. And I would very, very much enjoy being able to talk to any of you about this over the next couple of days. The reason I put this up, the math that's here is very, very close to the math that we've developed. And this is math for load balancing on existing circuits that we're already doing. We do this for load balancing. We do it for traffic stability in order to avoid chaos on certain of our circuits. We already have it. We have just never looked at it from a pure security standpoint. So analog network security for me has been an eye-opener. It allows me to look at the world in a totally different way. Every time I have a discussion with somebody, I go, well, what about the time factor? What about time? How does that fit into the equation? Because that automatically brings in an analog function and not any longer looking for a purely binary answer. These are the tenets, these are the rules, these are the fundamental pieces that I find to be exceedingly valuable. And I know that in 45 minutes I have not done this justice, but I hope to have gotten you to think maybe a little bit that looking at the world in a completely different way than we have in the past will offer us something of a path forward. And I really hope to have an opportunity to speak with many of you and for you to challenge me and for us to discuss how well some of these may work. So I want to thank you very much. Welcome to Hack in Paris, and let's all have a ball this week.